welcome all this morning. I welcome you to the third IMSC Distinguished Lecture given by Professor Vijay. It's a pleasure to have you here. So before I hand over to Professor Meena Mahajan, who would moderate today's talk, a couple of announcements. This talk is being streamed live on YouTube. So those who have questions over YouTube, you can type in the comments box. One of our colleagues is monitoring the questions. At the end of the talk, those questions will be taken up by the speaker. With that, I would request Professor Meena Mahajan, who will be moderator for today's talk. Meena.
Hello, everybody, and welcome to this event. It's my great pleasure to invite everybody here to this lecture, which is a lecture in the AKAM series. So, IMSC has had this series of talks on the occasion of the 75th year of India's independence, AKAM. And we've had a few distinguished lectures before this also, but this is the first time we are having a speaker here in person, and it's with great delight that I welcome Professor Vijay Vazirani here to give this talk. Since he's here in person, it will be easier for us to meet him and interact with him after the talk as well, as opposed to online. So, very brief introduction about the speaker. He is currently a distinguished professor at the University of California at Irvine. He earlier did his PhD at Cornell, his undergrad at MIT. In theoretical computer science, he is a very well-known name because of very deep and fundamental contributions he has made to many areas, in particular in algorithms, algorithmic matching theory, and approximation algorithms. He has written a textbook which most of our graduate students have seen and used at some point or the other. And for the last several years, he's been working in algorithmic game theory, in particular online matching markets. In complexity theory, which is a core course for our graduate program, he has made very nice contributions discussing how to use randomness to isolate solutions. And this is one of the key results that we use in building up a whole infrastructure of results. So for the computer science people, he's already a well-known name. For the non-computer science people in the audience, I mean, what more can I say beyond this? That he's a leading figure. His contribution to the area of algorithms and complexity theory are very wide and fundamental. His book is there in our library in case you would like to take a look. And today he is going to tell us about matchings. I think matchings is his all-time favorite problem. He started very early on working on matchings and has been returning to it in various flavors of this problem over the years. So today in particular, we have a very trendy buzzword there, Adwords. And it's my pleasure to invite Vijay to come and tell us more about this.
So it's really an honor to be here. And I thank you all for coming. Awesome, yeah. So I'm going to talk about online bipartite matching first, and then the Adwords problem. So let's jump into the problem right away. So think of a bipartite graph which has n vertices on each side. One side is called the goods and the other side is called the buyers. So there are n goods and n buyers. The goods you have all available right in front of you, but the buyers come one at a time. And each buyer has a set of goods that she likes and wants to get exactly one of them or none, so at most one of them. So comes a buyer and let's say we match her to the second good or third good here. Comes a buyer, we match her, and then comes a buyer and both the goods are already matched. And you can see that if we had operated the algorithm in a different way, we could have made all three buyers happy. So in some sense the fault is ours, right? And in some sense the fault is not ours because we didn't know what the graph would look like later. So that's the whole goal. So the underlying problem is how to make decisions with partial information. So they are good at the end of the day. So you are always comparing to the best offline algorithm. And in this case, we call this a ratio of the matching produced by the algorithm divided by n, the competitive ratio of the algorithm. And this is the worst case. So among all graphs which have a perfect matching in all arrival orders of the goods, we want the worst case ratio. That's called the competitive ratio. And another way to define this competitive ratio, instead of taking the minimum over all graphs and all arrival orders, is to assume that there's an adversary that picks the graph and an arrival order and picks it in the worst possible way. And then we see what's the worst competitive ratio we got. So it's very easy to, so this algorithm that I gave you will produce a competitive ratio of at least a half. It will give us the matching that is half the size of the perfect matching. By the way, the requirement of perfect matching is not essential. We can also compare to the maximum matching in the graph. But it makes life a little easier to assume that the underlying graph does have a perfect matching. So it's very easy to see that the greedy matching algorithm, because it's greedy because if it can match a buyer, it will match. So this will be a maximal matching, and maximal matching is half the size of a maximum matching, so it gets half. And let me show you that the adversary can also force us into a half. So the adversary gives us the first buyer with these two edges, and our algorithm matches to the first one, then the adversary gives the next edge like this, next buyer and edge like this. So we got one matched edge, whereas the adversary could have matched two edges. And then if we match to the lower good, then the adversary gives the next buyer like that. And again, we got 1 for 2. So we always going to get 1 for 2, and the competitive ratio is at most a half. So it's exactly a half for any deterministic algorithms. So the only way to do better is to introduce randomization into the algorithm. Okay, and now the competitive ratio is defined to be the minimum over all graphs of the expected size of the matching produced. Okay, so in this case, the adversary first picks the graph and the arrival order, and then the algorithm flips coins and executes and finds the matching. Okay, so how much better can we do with randomization? That's the question, because if we get only half the matching, you'll see that half is really, even if we get some constant fraction more than half, it will make a lot of difference in certain problems, like the Adwords problem that we're going to talk about. Really a lot of difference. So here's a straightforward randomized algorithm. You match each buyer to a random available good. So among all the goods that the buyer could get, which are still unmatched, you pick one at random and match her. I'm still audible, right? So let's see how well this algorithm works. It's very simple. Everybody understood the algorithm, right? Match the next incoming buyer to a random available good. So here's a bad example for it. And I'm showing this example not by showing you the n by n bipartite graph, but the n by n adjacency graph, which has a row for each good and a column for each buyer, and the arrival order of the buyers is like this, from the nth column to the first column. Okay, and if you observe this adjacency matrix of this graph, it has a perfect matching sitting on the diagonal. These ones form a perfect matching in the bipartite graph, and it has an n over 2 by n over 2 sub matrix here, which I will call the trap. And you'll see why I'm calling it the trap. These ones. And then besides that, there are only zeros here in this matrix. Now, the columns are going to come n, column n first, then n minus 1 and so on. That's the adversarial order that the adversary gets picked. And it's very easy to see that if out of the first n over 2 columns, k of these n over 2 columns match into the diagonal, their own diagonals, then the size of the matching produces n over 2 plus k. So the reason is that the first n matches to the diagonal, the more matches you get to the last and over. Exactly as many more as the diagonal. Okay. But the diagonal matches will be very few, only order log n, because most of the time the column will be matched to the graph. If it's taking a random one in that column, there are n over 2 ones for the first column, there are n over 2 ones in the graph, and one only is the good one. So most likely it will match to the graph. And then the next one will have maybe n over 2 minus 1 columns in the graph, and so on. So most of the time it will get matched in the graph, which are all bad matches. The good matches are going to be order log n, which means that this size of the matching will be n over 2 plus order log n, which is minuscule addition, increment over a half. Right? A half plus little of 1 is the commutative ratio. So we didn't do very well with this scheme of randomization. And so the question is, how should we change the randomization? And this seems like a very natural algorithm that we're thinking about how can you do better, right? So how can you do better? First, you have to study this bad example as much as possible, see what works there. And second, you have to design an algorithm that's not just dealing with that example, but what is going to deal with all examples. Okay? If you fine tune it to that example, that's not the way I works. So one way to think about a heuristic for designing an algorithm is that good algorithms are minimalist. Very few lines of So any questions or any comments as to what algorithm you propose? It won't be easy to come up with something. Okay, so there are lots of nice algorithms that are 3 and 4 lines each. Maybe you permute the goods at random ones, and as these buyer terms, you match it to the highest available good, highest good that will match. Okay. So let's see what happens with this bad example. So we are going to randomly permute the goods. That means that these rows will get randomly permuted. So half of this math will go down approximately, and half of this nice stuff will come up. Okay. And the arrival order of the columns is still that same one. And when this column in the first row to arrives, it looks something like this. That it has some ones coming from the top and over 2 rows, and some zeros coming from the bottom and over 2 rows. But because the rows have been permuted, these entries appear in some order like that. And some traces will be diagonal entry of this column, which are that one. That's the nice match. The bad matches are these ones above. So when this column arrives, it's going to look down to look at the first one that is still unmatched and match to that. Okay. So what happens is that these ones and zeros versus in all the previous columns. So the previous column also will have 1 exactly here and 0 exactly here. They won't, of course, have this diagonal 1. They'll have their own diagonal 1 wherever it is. Right? Each column has its own unique diagonal 1. But the point is that every bad match that happens early on increases the chance of a good match now. Because if there's a bad match early on, then this one will get matched off. The red one will get matched off. So if there are 2 bad in this case, there are 2 bad matches early on, then for sure this column will be happy and will get a good match right in the diagonal. Okay. So because it's a general audience talk, I'm not going to give a proof of this algorithm. But let me just say one word why this works. You see that? It is self-correcting. The errors made early on ensure that later on good matches are made. But also you can see that half the diagonal entries will seep into the first half of the matrix, and those diagonal entries are likely to get matched. You always stuck at over the plus order. And in fact, no matter which graph you took, it will be 1 minus 1 over e plus 1 minus 1 over e. This is the combinatorial ratio established for this algorithm is called ranking. So this is work done by Prof. Vazirani. And it was done in 1990, before the internet even came about. And before there were any computer science that has to do this problem. Now there are lots of problems. So, and this is optimal. So, we also showed in this paper that can beat 1 minus 1 over by other than by a little of 1 term, which is also probably a figment of the proof at this point. So, this is all very nice, done 31 years ago, except that the proof at that point, given in that paper, was too complicated, too difficult to understand. Very few people got into it. And then over the years, many people started improving, making the proof simpler and simpler. First, work was done by Gagan Goyal and Aranek Mehta, two of my students in 2008. And then Claire Matthew and Brent Baum got a further simplification, and by now many people started understanding the algorithm. And then Nikhil Devarnu, Kamal Jain, and Bobby Kleinberg in 2013 gave a randomized primal dual framework, which really made the proof much simpler. Now it was very widespread. And more recently, Michael Feldman and Amos Fiat and two students, Alonian and Siegel, they gave an economic interpretation to this framework. They also organized the way the charging is done a little bit more better way, and by now things have become very elegant, very easy to understand. And that's the proof I would give today to the theory people appropriate to take you into the proof right now. So I'll go to other things. I'll just say the following, that the algorithm ranking has to be redefined like this. This is an equivalent definition of ranking. Namely, every good J picks a weight Wj in the continuous interval from 0 to 1 at random, and computes e to the Wj minus 1, which is defined to be the price of the good. Yes, I told you that there's an economic interpretation. In that interpretation, these prices are really viewed as prices, and buyers get utility 1 from the good that they like, one utility. But then think of a buyer as paying this price for the good, and so she wants to obviously pay the minimum price and get the maximum utility. And so she looks for the minimum price good among the goods that are left over, which she likes. Okay. And this is identical to ranking. Why? Because with probability 1, all the prices will be different, because we are picking price weights from a continuous interval. So all the n prices will be different, and if you sort the prices, you'll get a random permutation of the goods. Right? So in other words, every buyer is going to be matching to the highest available good in that particular order once you find the price. And so every buyer will match to the cheapest available good. This is identical to ranking, but these prices are random variables which give us a lot of power to make a very simple analysis from here on. So if you know some elementary probability theory, undergraduate level, you know your expectations and random variables, you can jump into the years now, really, literally, and moved to what are called matching markets. And here's a whole slew of them coming from every walk of life. You have seen them before, for sure. Certainly you would have seen Uber, Lyft, and Airbnb, and so on and so forth. Okay, so it looks like a mess. So I want to classify these markets in three classes. These are the pre-internet markets, where in the first one you match medical residents to hospitals. It's a very big market. The second one is matching students to schools. So if you think of a big city like New York City, which has 100,000 students every year that needs to be entered into schools, maybe hundreds of schools, there's a big, massive question: who goes to which school? How do you do the matching? So that you also respect their desires and the limits of how many students each school can take, and so on and so forth. And it's all done in a computerized way using an algorithm. I'll talk about it in a moment. And then there's kidney exchange. So these are, you can see these are markets which have financial or economic as well as sociological impact. And then came the internet, and all of a sudden completely new markets opened up. And this whole area of matching-based market design took a new turn altogether with huge impact. So the Adwords market I'll talk about in great depth, so I don't want to mention it now. But it basically matches keyword queries to advertisers. And I'll show you in detail. You probably know about it inside out. Right? How many people, by the way, here have heard of this company called Google? Yeah, I thought so, right? I mean, we are in India, right? In Mars. So, okay, so that was a joke anyway. So, you didn't have to raise your hand. I knew that. So, anyway, the point is, you would have seen the Adwords market, whether you know it or not. But you'll find out what it is in a moment. Then there's Upwork, which matches people seeking work to employers who have small jobs to do. Display ads is just like Adwords, except that you put ads on the page. So it's a market in the vein of Adwords. It's a digital display advertising market. Mechanical Turk is like Upwork and Match.com. Everybody here knows, right? Only people know what Match.com. And then there's mobile computing, and you have Uber, Lyft, ride sharing, where two people who come proximally and almost simultaneously and want a ride, how do you match them up so that they share a ride? Airbnb, I don't know if it's here, but you match people wanting hotel rooms to people who are renting rooms in their apartments or houses or whatever. So very many markets from all walks of life, as I said, and this is the new wave of markets in matching-based market design. And there is one market here that I didn't put down, which is of relevance to everybody here in this room. You know what that is? Yeah, who said that? Have you heard this before? Yeah, good. The academics are excellent. Good. I really get that answer. So, indeed, the academic job market that everybody here is worried about. You're worried about it, right? Okay. But even the faculty are worried about it because they have to place their students. So, why did I not put it in this bunch? Because this is the most badly behaved market. So that's what matching markets are. In what sense are these markets? So here's a very nice way to look at it. What are the markets? Matching markets are markets because they aggregate information held by participants, which is what markets do. The market that you go to get whatever goods is also doing an aggregation of all the buyers to all the sellers, to all the goods and the prices. Okay. And this is was given to me by Algorithmic, who's one of the two Nobel laureates from 2012. Lloyd Shepley has passed away with that. And this prize was specifically given for matching the market. And last year, Paul Milgrom got the Nobel for different work, but he has also made one of the So I want to go back to the early years of So, I just want to say that this is, I know this is unusual in the field of game theory and economics to get that kind of stuff. Most of the solution concepts given by economists and game theorists do not have this kind of and in fact are very sensitive. Like extreme safety value, marketing and so this is unusual. And not only is there a fundamental and algorithm, but there are incredible properties of stable matches. And most people here would know what stable matches is. Very basic theory to understand discrete matches. We know those things. But these macros, as many of you would know, namely, if you take let S is a set of all stable matchings, and take a partial order on this, a very natural partial order. I want to find it. This set. Then the set with this partial order of the finite distribution lattice. I won't define this notion either, but I'll just figure that what it is. So a finite distributive lattice has two special elements, the top and the bottom. And in this case, it's the resident optimal and the hospital optimal matching. One is best for the residents, one is best for the hospitals. And every finite distributive lattice satisfies the conditions of Burkhoff's representation theorem. And therefore, many other nice things follow, including the existence of what is called rotations, which help traverse this lattice from the top to the bottom or from anywhere to anywhere. And you can get the set of rotations and do the traversal all in polynomial time, even though the set of stable matchings is exponentially large. So the lattice could be very large, but you can go from the top to the bottom in polynomial time and see all the stable matchings on the way as you go from something that's resident optimal to hospital optimal, gradually making it less and less optimal for residents and more optimal for hospitals. Okay. And then Burkhoff also, Garrett Burkhoff, the professor at Harvard at that time, he gave the Burkhoff polytopes for perfect matchings in bipartite graphs. And similar to his polytope is a polytope of stable matchings. And through that you get linear programming formulations for stable matching, another polynomial time algorithm for finding a stable matching. So there's a lot of stable matching, a lot of polynomial time all over this thing, all over this problem. And there's a lot of polynomial time because there's a lot of beautiful structure that this problem has. And you can ask, why does it have this structure? I believe it's because it comes from this place. So, beside algorithmic properties, it also has great game theoretic properties. For instance, stable matching is satisfies the notion of a core. Core means that there's no subset that needs to has any incentive to succeed. I won't go into these definitions. Anybody who has learned stable matching in undergrad would know what this means. And more importantly, for the proposing side in the deferred acceptance algorithm, the proposing side has no incentive to cheat because they'll get the best match by reporting truthfully. So it's dominant strategy incentive compatible, and that means that it opens up the stable matching to unbelievably many applications. And in particular, this is where the work of Adwords comes in for school choice, matching students to schools. Students who are entering school, I think, right in the first grade or so. So that is so here's another problem called maximum matching that's useful in another kind of application called kidney exchange. So you know that you have two kidneys and you can survive on one. So if somebody has damaged both their kidneys, then they want to get a new kidney, and they go around asking some, their friends and relatives for a kidney. They may be able to get a donor, but then the two they have to match in a number of parameters, and if they match, then the donor can give the kidney to the recipient. But matches typically don't happen, and then what you have to do is you have to find a donor and a recipient that don't match to each other, and D prime and R prime that don't match to each other, but D can give to R prime and D prime can give to R. So if this nice thing happens, that you have two pairs which cannot give, but the two pairs can give across, then you can do the exchange. So D gives to R prime and D prime to R. And then you have to do it all on the same time in one hospital with 4 operation theaters, because if you do this exchange on the first day, D gives to R prime, then D prime may say, hey, I don't want to give my kidney anymore. And that's going to be a fiasco. So you want to do these kind of foursomes all at once, and you have a huge market with many people with many donors of kidneys, and you want to find a maximum number of these foursomes. And basically, how do you find them? You create a graph. Vertices are DR pairs, and edges when you have 2 of these pairs that can form a foursome of this kind and find a maximum number. So that's another matching problem that gets used here. And I just want to say that in the second life of matching markets, online bipartite matching, which you saw as the very opening problem, and its generalizations of the algorithmic platform. Why do I say that? So Adwords is a direct generalization of online bipartite matching. I'll tell you why. Upward is a generalization where think of both sides arriving online. So the showing to this user of who typed Vioxx. Okay, which advertiser to put out there? That's a problem that Google faces all the time. And the way Google was solving this problem was just to give it to the highest bidder, and that's called an efficient solution in economics because whoever is willing to pay the most is going to use this opportunity the most, and it's going to be best for the economy. And that's how things were done for the first couple of years of Google. And so basically, in other words, give it to the highest bidder, and this is a greedy algorithm, right? And we will assume that we're going to show only one ad, even though you saw many ads there. That's all, we can talk about those bells and whistles later. Let's look at the basic mathematical problem. So this is what they were doing. And, and so give it to the highest bidder. So you would have wanted to see pharmaceutical companies here. But what you see here is lawyers, 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 and lawyers. Okay, what happened? What happened was that Vioxx was causing massive heart problems to some of the people who were taking this drug. And the lawyers decided that before these patients die, some money should be made off of them. Okay, so they've been bidding $50 to $100 to be here instead of the 25 cents that the drug company can dole out. Okay, so when you give it to the highest bidder, what happened? Which is good. It's good for the economy. So this solution was being used, but there's a problem with this solution. Namely, when you go out into Google's website and set up your account to declare your keywords and how much you're going to bid, you also declare the daily budget because you don't want to be wiped out at the end of the day with all the queries you got. Okay, you don't want to be overcharged at the end of the day. So this daily budget completely changes the picture because you cannot just give it to the highest bidder anymore, right? You have to take into account the budget. So let me show you how bad things can get. So suppose there are two bidders, they both have $100 for today, and there are two kinds of query keywords that they are interested in, or rather, the first bidder is interested in two keywords, book and CD, and bids $1 for each. The second bidder is bidding 99 cents for book, nothing, has no CDs to sell. Okay, and let's say that today 100 book queries come first, and then 100 CD queries come. So comes the first, and we'll look at the algorithm greedy. So comes the first book, and it goes to the first bidder. The other 99 queries also go to the first bidder. And comes the first CD, and bidder 1 has completely spent the $100. And bidder 2 doesn't want CD query, so it goes waste. And all these go waste. So the total revenue of Google is $100. But if it were to send the first 100 book queries to the second bidder and the second 100 CD queries to the first bidder, Google could have made 199, so twice as much. So basically, it can be forced into half the revenue, half the optimal revenue, half the optimal offline revenue. Of course, it has to do it all online. It has to do it right away, right? It doesn't know what queries are going to come later. So very much the same spirit as online bipartite matching. Okay. So what should we do, right? Except that this is a much more general problem than online bipartite matching, as you can see, right? So we were faced with this very nebulous and general problem in 2005, and the first thing we did was we being Arnab Mehta, Amin Saberi, Umesh Vazirani, and I. And the first thing we did was to give a simple framework that captures the essential features of the problem. Okay, so that we could analyze it mathematically. And we were very much aware of the fact that we could be solving a large LP to figure out who to give the queries to. because that large LP will take very long time to solve. So the solution had to be very, very lightweight, because Google's answers to the query comes very, very fast in milliseconds. So these ads also have to come up in milliseconds. Okay. And this whole problem is very important, because for the first time, small advertisers, small budget advertisers got a way of advertising the goods through Google. They cannot put up big billboards, right? Your corner pizza store or something. They cannot put up a big billboard saying pepperoni pizza. Okay, so and there are lots and lots of bidder advertisers in this other fat tail of the distribution. So that's where lots of Google's revenue lies, and you have to deal with all of this stuff very well. So this is a general problem that we define. It's called the. So you have advertisers sitting. You know who they are. Google knows who they are. Okay, and each one has bid something for queries that they are interested in. Okay, and assume that there's an underlying bipartite graph at the end of the day. At the end of the day, it will become clear what that bipartite graph was. You will get only queries online, just like the buyers were coming online in online bipartite matching. And each time a query comes, there's a bunch of advertisers who really want this query, and they have bid different amounts. And the question is, which of these advertisers does this query choose, or does Google choose to show with this query? Right? That's the big question. And of course, the budgets should come into the picture. Otherwise, we'll be forced into a half, which could be leaving too much money on the table. Okay. So at that point, we did try to extend ranking to this problem, but that was very, very difficult. We didn't get very far on that. But there was another matching-based problem called online B-matching, which is the following, which can be thought of as a special case of Adwords problem, where each advertiser has B dollars for a very large B, and the bids are either 0 or 1, just like online matching. So B is very large. And Kalyan Sundaram and Cruz had given a 1 minus 1 over E deterministic algorithm for B matching. And very nice algorithm called balance. And the main idea is give it to that bidder who has spent the least. So when a query comes, look at all the bidders who are interested in this query, find out the bidder who has spent the least so far, give it to that. And if you keep their spending balanced across the day, you're sure to get 1 minus 1 over E, even against an adversary. And it's optimal. You cannot do better. Just like online bipartite matching, ranking is optimal. So this is our algorithm for Adwords. You compute the following. You don't just make use the bid, but you multiply it by this function f applied to a fraction of budget spent so far. Okay, and this achieves, and it's a deterministic algorithm. It achieves a competitive ratio of 1 minus 1 over E, assuming that the bids are very, very small compared to the budgets, which they are in balance. Okay, so we are just taking balance and moving it up one level using LP duality and so on. Okay, and you can see this is a very lightweight algorithm. At the end of the day, you're just computing one function of the fraction of the budget spent. So you just keep around budget spent and apply f to it, multiply by the bid. So it's very lightweight, it's optimal, and that was exactly what was needed. A simple minimalistic solution, and so it had huge impact. Of course, no Google is going to tell us what impact it had, but we can see that it had impact. And there's something called bid scaling in that industry of search engine companies, which is scaling bids not necessarily through this function f that I gave you, but through other heuristic means that used by all the search engine companies today. And this is the benign agent with deep pockets that sponsored all these papers on online bipartite matching in Adwords, and a huge amount of work got done because they had limitless funds and they wanted to leave no stone unturned because all of these various results many of them got used for various ad products. By the way, do you know what the digital ads spending is per year worldwide on just digital ads? Every year, worldwide, more than $500 billion. So here is the question that I came up with when I saw this very simple algorithm of ranking, which we could not extend to small bits or to general 15 years ago. Namely, can I extend ranking to these problems? And I went some distance, but not the whole distance. And why will become clear in the next talk that I'll give. And so there's this problem still left to be done. I don't think it's easy, but you're welcome to look at it. But if you really want to make a difference, this is better. Think of your own nice problem. Thank you. I hope I didn't run over time.
No, not at all. Yeah, thank you very much. So we do have some time for questions, and those who are on YouTube could also, if they've posted their questions on YouTube, I will take them. I will read them out. But first, let us look at questions coming from people here.
I have a very elementary question. I hope you can.
Those are the best.
It's about you said this matching.
Sorry?
You mentioned about matching using some algorithms. These are all deterministic, or you can also have some.
So online bipartite matching is randomized.
Okay.
Even within, so maximum matching is deterministic when you do it sequentially. When you do it parallel, NC, randomized. No deterministic algorithm is known. These are big open questions. Then there are so many other questions regarding matching. Count the number of matchings. That's a random. There are randomized algorithms for some problems, not known for others. So it's a mix of deterministic and randomized algorithms.
Yes. Can I ask?
But stable matching is all deterministic, no randomizing.
Okay. Related question. Do you also use machine learning and things like that in any of this matching?
Use a lot of that because it's not okay to just look at a worst case analysis. You have to also look at the historical data, what happened yesterday and 2 months ago and 2 years ago, and learn from that. So yeah, ML is used a lot.
Okay, thank you.
Maybe it's off the mark, but I was just wondering if this 1 over E, 1 over 1 minus E has anything to do with the derangement problem.
Derangement.
So if you have a permutation, then the probability that has no fixed points.
Yeah. So 1 minus 1 over E occurs in 10 different places. I don't know that there's a common reason for that. In online algorithms, there are at least 5 different flavors of algorithms that have 1 minus 1 over E. Then there's the secondary problem, that's 1 minus 1 over E. There's so many, ski rental problems. Every now and then somebody asks this question, but they don't fail to see that underlying reason. I don't.
So we don't know why it's the same.
No. What is the commonality among all these 1 minus 1 over E's? I don't know that.
Another question, I don't know, probably you said it has something to do with probability theory. Why did you take E to the minus?
That has been optimized. That has been optimized very much. You could have taken the uniform distribution and got stuck at a very low competitive ratio. It has been optimized to give you the best competitive ratio. And as I said, this is the second algorithm a reformulation of the previous algorithm, which did not apply any function like e to the x minus 1.
But I thought only the ordering between the prices mattered.
Say that again?
I thought only the order amongst the
So
prices.
the first algorithm was just a matter of ordering the goods.
Oh, okay. Now
The second algorithm is a restatement equivalent algorithm that uses this function, and because of this function and the random variable Vijay, it has a lot that random variable gives us a lot of power to arrive at a simple analysis that can be taught to even undergrads. The other analysis is very difficult.
Thanks.
Thank
But
you.
you already have a job, right?
Yes, currently over here.
Sorry?
Currently over here.
Oh,
I'm a
okay.
faculty here. Okay, so it's just a sort of a clarifying point. The original setting in which ranking was defined was the standard matching setting where one query can get matched to at most one advertiser, right? But with the B matching case and the other one, Adword, you allow more like a capacitated thing, right?
Right. You
So
can so this person has B dollars and so wants B queries at most B queries at the end of the day. May or may not get all B.
So that's what you were referring to, the generalization, as in
So
extending ranking.
So let's go back. Wait. So B matching is this problem.
Yes.
Adwords is where the budgets are arbitrary among the advertisers, and the bids are not 0 or 1, they are arbitrary, 0 or some Bij.
Right, and so the main thing is that ranking though was applied to the case that was a one-to-one matching sort of scenario, like at most one person
Right,
to get.
yeah.
So these are all more generalized,
Of course.
capacitated notions of that.
Yeah,
So is that where also the technicality lies in extending ranking to these?
This becomes it. So I'll just tell you one fact. It's very surprising. So this problem general Adwords with arbitrary bids and arbitrary budgets and arbitrary underlying graphs. So if you just apply plain old greedy algorithm after ignoring the budgets, you get a half. Doing better than a half was a big open problem, and somebody in 2020 had a Fox paper, 60 pages long, giving 0.5016. So improving half to 0.5016. And from there to 1 minus 1 over E is a large place to go. I don't know if we'll ever get there. So that was my hope to use this better analysis of the easier analysis of ranking to go as far up as possible. But I got stuck in other technicalities, and that's the subject of the next talk.
Okay, thank you.
Any other questions?
Hi, you mentioned the academic job market, maybe in a lighter vein, but there is one additional complication in that market, which is the two-body problem, which means you might have two nodes which have to be assigned to the same.
So that arises also in the resident market.
Okay, yeah.
So you know that in the 50s, most doctors were men, and again gradually women entered the field, and then in the 4 years that you, or 5 or 6, or I don't know how many, that you study medicine, you're only studying medicine, you're not doing anything else. So they were getting married to each other right there in their studies. And now at the end of their studies, they want to go to become residents, hopefully in the same city, or if not in the same hospital. So now you're faced with a new kind of market where you want to solve the two-body problems of these residents as well. And it became anti-complete, okay, to solve. But then there are heuristics to be given to place as many couples as possible, and that's done today. All of those algorithms are being used today.
Okay, I didn't realize this was a already studied problem.
Very
And
much.
do you feel that it's actually worth it having an online academic job market for people who say there are two of us, we want a job, but we want to be in the same place,
So
and
it's
the
not-
machine assigns you
academic
somewhere.
job market is not as easy as resident market. Because what each department wants is so unique, and what each professor wants is, professors are very difficult to please, right? So more so than doctors, maybe. I don't know. Seems to imply that. I don't know. I don't want to make any conclusions here, but those matches are very, very special purpose. So I doubt it that you can do any. I don't know. Many people have grappled over this issue, how to make this academic job market more efficient or better behaved. And there are some proposals, but not very powerful, not very big time proposals that hit the problem right on the head. So we're still waiting for a good proposal. Thank you so much, and
So are
see you
there,
for
any,
the next talk.
are there any more questions here right now?
Oh, one more.
Yeah, we're still having.
Do we still have time?
Yeah.
Thanks for the talk. So, in the algorithm that you're describing, so in some sense, you penalize every agent, on its spending. So, it's 1 minus e to whatever, but it's remaining, right?
Yeah.
I mean, that's something similar to what multiplicative weights does. So, is there an expert learning multiplicative weights?
Yeah. These connections have been explored. Yeah, good point. Yeah, but not directly. It's nothing to do with that exact idea. But people have explored those. Yeah, good connection to think about. If you come up with new insights, I'd be thrilled to hear about them. Nothing great right now.
Thanks.
Okay, I don't see any more questions here. So thank you, Vijay, very much. Let me call our director, Professor Ravindran, to give a brief thanks.
Oh, can I
Thanks for
step
that.
down?
No.
Thank you.
Of course. Yeah, I take this opportunity to thank Professor Vazirani for agreeing to give this wonderful talk. I don't come from physics. I come from physics background, but I don't know much about computer science. But the way he put it today about market matching and things like that, matching the markets, it's really quite illuminating, and I could understand actually. Thanks for your wonderful presentation, and I'm sure you'll have more interesting interactions with people here. Thanks a lot.
Thank you. Yeah.